Hey guys, today I want to go over the cosmology notes, and we're getting started in Unit 2 here. So about 15 billion years ago, or give or take a few, as science progresses, we tend to learn exactly when these things happened. Um, and as our technology increases, we're able to look further and further for these things. But there was a tremendous explosion that started the expansion of the universe. This explosion is what we call the Big Bang. At this point, all of the matter, energy, and space that ever was contained at one point. What existed prior to this event is completely unknown. We have no idea of figuring it out, but scientists are trying to. Um, this occurrence was not a conventional explosion, but rather an event filling all of space with all the particles of its embryonic universe rushing away from each other. So from this explosion, everything started moving outwards. And we'll get to why that's important and how we know that a little bit later on here. And basically what this explosion did is it laid the foundation for what we now consider to be the known universe. So over here to the right of the screen, you can see that I've pulled up the guided notes here. I'm going to try and see if I can type along with you, and we'll see how this works. So the origin of the Big Bang Theory can be credited to Edwin Hubble. If I can spell his name right here. So Edwin Hubble. Let's move on. So, Edwin Hubble also gave us Hubble's law. And Hubble's law states that galaxies are retreating from the Milky Way at a speed that is proportional to their distance. Basically meaning they're moving further away at a speed relative to how far away they are already. Okay? And how we know this is that galaxies have a red shift. They have a red tint when we look at them in a telescope or examine the light that comes off of them. There's a small faint light that comes off of things as they move away or they move closer. Things that have a blue tint are moving closer to you. Things that have a red tint are moving further away. And we'll see that here in just a minute. It might be easier if I were to highlight some things that make it a little bit easier for you. So Hubble's law, galaxies are retreating from the Milky Way, and these are the two things that go in over here. And the red shifts of distant galaxies show that the universe is expanding. Okay, let's move on here. So red shift or Doppler shift toward the red end of the spectrum occurs because light waves are stretched, which shows that Earth and the sources are moving away from each other. And this shift is clearly the Doppler effect. And I'm sure you've heard the phrase Doppler effect or anything like that if you've seen the show Big Bang Theory or something like that. Most notably, other than light, we can see the Doppler effect in sound. Most of you are familiar with the sound effect that a bomb makes when it's falling. You get that's what we call the Doppler effect. So as something moves closer to you, the sound gets more of a higher pitched. As it moves further away, the sound starts to develop a lower pitch, and that's just because sound waves have to travel either further or are closer to you. You can also hear that in the sound that a car makes as it's coming towards you. The sound starts to increase in pitch, and as it's moving away from you, starts to decrease in pitch. But we can move on here. So redshift or a Doppler shift, which goes in these blanks here, towards the end of the spectrum, and we'll cover the light spectrum a little bit later if we get the chance, so that sources are moving away from each other. Moving on here. So to help visualize the nature of the universe, imagine a loaf of raisin bread or anything that has small little specks in it. You can even take chocolate chip cookies, for example, but they call it the raisin bread analogy here. And simply what happens if when you have the dough, everything is clumped up and close together. Think the chocolate chips and the cookie, they're all close together. But as you bake the cookie, the whole thing starts to spread out and the chocolate chips start to expand as well. Okay, so the Big Bang Theory is what goes in this next one, states that at one time the entire universe was contained in a dense, hot, supermassive ball. Then about 13.7, we said 15, there's varying scientific debates about those things. We'll accept either one, anywhere between 13 to 15 billion, it's fine. a violent explosion occurred, hurling this material in all directions. So just one giant explosion, everything's moving out. Okay, and you can input those two things here, the Big Bang Theory, 13.7 billion years. Okay, here's a enlarged graphic of that. Okay, so supporting evidence of the Big Bang Theory, we just talked about redshift. So the redshift of galaxies goes here. Redshift shows that the Big Bang Theory is expanding. Okay, so scientists discovered a type of energy called background radiation. We're able to measure radiation that's coming out, or cosmic radiation that's coming off of space. And scientists think that this radiation was produced during the Big Bang. That's the prevailing scientific theory right now, the paradigm, if you will. And those are here, cosmic background radiation, and the Big Bang goes here. So moving on, the Big Crunch. So the future of the universe follows two paths. The universe will expand forever. That could happen. Expand forever until it's nothing. So expand. And the outward expansion will stop, and gravitational contraction will follow. So there's two things. Either the universe is going to keep getting bigger and moving away from each other, everything will, or eventually it'll reach a point where the force that's pushing the galaxies and everything else away will stop and not equal the gravitational force of it pulling it back together. Contrary to popular belief, most people think that there is no gravity in space. I'm here to tell you that there is. When we see astronauts floating in space, they're not actually floating because there's no gravity. They're floating because they're in something called free fall. And during free fall, objects are weightless. And I'll show you a small demonstration of that as we move on. Okay. So the outward expansion will stop, gravitational contraction will follow, and we'll keep moving on here. Okay, so the solar system, we're going to get to all the planets here, and you probably remember that from 3rd or 4th grade, but we'll give a brief overview of it. And how did our solar system form? Okay, so it began to look like our solar system about 4.6 billion years ago, somewhere around there. Okay, the nebular theory supports this. Okay, the sun and the planets formed from a rotating disk of dust and gases. Began to look like our solar system 4.6 billion years. The nebular theory, okay, and that also helps us define what a nebula is. And it is a cloud of dust and gas in space, okay, and we'll do some an accretion demonstration in class as well, and I'll show you about that. And you can see what that is here. So remember, any two objects in space attract each other, okay. What you need for a gravitational field is to have mass and distance between the objects. So we call that gravitational attraction, and that can go here. An accretion disk is a rotating disk of dust and gas that eventually collects around other massive objects. And the growth of planets began as solid bits of matter that then collided, clumped together, smashed into each other until they were one, and we call that accretion. We started off with planetesimals. Moving all over the notes here. And those are small, irregular shaped bodies formed by colliding matter. Okay. After that, planetesimals became protoplanets. Okay. Protoplanets go here. And the sun initiates nuclear fusion, and we'll talk about the difference between fusion and fission as we get into energy a little bit later on. So solar wind and radiation swept out the remaining gaseous material from nebular disks. After that, the inner planets became heated and melted, and their primordial atmospheres were lost. And the Jovian planets, which are the planets outside of the asteroid belt, maintained gaseous states, and because of their great masses, were able to keep that atmosphere and composition of the present-day sun. And we'll talk a little bit more about this stuff later on, but just wanted to give you a brief overview here, and both of those things go in this. Okay, so inner planets and the Jovian planets. Remember, Jovian planets are simply the planets outside of the asteroid belt. Furthermore, here you can see some questions that'll help answer things, and I'll scroll through these really quickly.